Hi, everyone. I'd like to start by thanking the organizers for a great opportunity to talk about our work. I'm Suhail, and today I'll be talking about the Hubble constant from type 1e supernovae in two broad themes. Firstly, from the local distance ladder, and secondly, from the strong lensing point of view. So the first ever strongly lensed type 1e supernova with resolved photometry and spectroscopy. And they'll both be banded together within a single theme of ongoing work with this wiki transient facility. I'll also be talking a little bit about some recently concluded work on looking at the impact of dark energy model assumptions on the local value of H0. So I'll start with a brief motivation for both of our works, or both of the themes that I'll be talking about today, and why it is that we want to explore in multiple themes. Firstly, I'll talk about the recently concluded work on the dark energy model systematics and how that impacts the local value of H0 inferred from the distance ladder. And then I'll talk about the sample of year one type 1e supernovae from the Zwicky transient facility. So that's the sky distribution of the supernovae on the ZTF field grid. In the second part, I'll talk about strongly lensed type 1e supernovae, focusing on IPTF 16GU, the first resolved strongly lensed type 1e supernova, and what interesting physics as well as like what we can learn about cosmology from lens supernova and the ongoing search with ZTF. So very simply, like we have the Hubble tension, which is an extremely significant problem in modern cosmology with very like fundamental implications for particle physics and cosmology. So it could be additional species of relativistic neutrinos, could be varying electron mass, could be some other like dark radiation in the early universe, or it could be some sort of late universe explanation. Now, with the current data, there's a lot of these different studies combining different probes where we don't have a singular explanation for what it could be, but we don't want to go into details about what could be cosmological implications of the Hubble tension. What I just wanted to emphasize here was that what I wanted to talk about today is mainly unaccounted for sources systematics and looking at like what could be potential sources systematics. Do they actually impact the value of H0 from the local distance ladder at the level of the tension which we see, which is around 9 to 10%, and also completely independent probes of the absolute distance scale. So these could be, like as we'll hear in other talks, gravitational wave standard sirens, also like independent distance ladders. But what I'll be talking mainly about is time delay distances from lens transients, specifically lens supernovae, and explaining why they're interesting complements to the existing work done by using lens quasars. So before I talk about what we specifically wanted to look at with respect to the distance ladder and calibrator and Hubble flow type 1e supernovae, just briefly, how is it that H0 is measured from the local distance ladder? So the Hubble constant is measured by calibrating the absolute luminosity of type 1e supernovae, which are bright stellar explosions. They can be calibrated and standardized to a very small dispersion in their peak luminosity in the optical wavelength. And these are calibrated with secondary distance indicators, which are typically the Cepheid variables at tip of the red giant branch stars, but could be also other potential calibrators like Miras or JAGB stars. So the distance ladder is typically truncated to a region where impact from other cosmological parameters like the deceleration parameter, or in a particular model, say the matter density or the equation of state of dark energy, is minimal. However, there is an assumption on what this value should be, and this is fixed when doing the computation. And that's essentially what we wanted to test. Like if we do have some dark energy model that is non-standard and has very peculiar behavior compared to the standard cosmological scenario of lambda CDM, would that cause a different inference of the Hubble constant? And essentially, how robustly can we infer this by having a combined covariance matrix of not only the nearby Hubble flow and calibrator supernovae, but the calibrator supernovae and everything that goes all the way out to redshift around 2. So this is very complementary to robustness tests done at the lower rungs of the distance ladder, as I listed here. So what we did in our study was basically take lots of different non-standard dark energy models. So some of them were just phenomenological extensions. For example, the WCDM model where we just have the equation of state free. And then we had like lots of other like more complicated models like the biometric gravity model in which instead of just a single metric, there are two metrics with a carefully constructed interaction term. And that's so to avoid ghost modes in massive gravity. There's also dynamical dark energy models like the slow roll model or thawing quintessence. And we also looked at models that do not have a smooth equation of state. So these transition models where there's a lot of dramatic transitions at low redshifts, so below 0.1, below 0.02. And this was originally like a potential explanation for accelerated expansion, but because of the lack of data at the very, very low redshift, they could not be constrained because most of the transitions would happen below the lowest redshift type 1e supernova. However, now that we're combining the calibrators along with the Hubble flow supernova, we essentially have like 1 point at redshift 0 by design, because the calibrators are not like a redshift distance, it's an independent distance coming, in this case, from the Cepheid variables, because we wanted to look at the shoes calibration. So now we can test these models as well. So we have a single combined calibrator plus Hubble flow covariance matrix, and we can also like combine this with other probes to do dark energy models. So we wanted to see what is the impact on H0. So what we see here is, and this is all the solid lines in the plot on the right-hand side, that even for very, very non-standard cosmologies, the maximum shift between the highest and the lowest value of the Hubble constant is about 0.7%. So that's not a significant shift with respect to how large the tension, which is of order 9%. So even with all these various different transitions and like non-standard cosmologies, we don't see that the absolute calibration of H0 changes by a significant amount. And if we look at the comparison of statistical only and statistical plus systematic uncertainties from the supernovae, both in the calibrator and the Hubble flow realm, the shift is about 1% in the value of H0. So again, not very significant relative to the size of the tension, but in order to get to like the 1% level in the distance scale, this would be something that is important to quantify and improve upon, and like have a better understanding of photometric calibration, as well as the dependency on host galaxy properties and other sources of systematics, from like having a better intrinsic scatter model, for example. So this is interesting both from the standpoint of how to move towards the 1% when improving the distance scale, but also to have like a combined probe of dark energy model studies, so we can use this in combination with baryon-acoustic oscillations in the CMB in order to do dark energy model studies as well. So what we also did was, like in the previous plots that I'd shown, we had model assumptions on what could be driving accelerated expansion. But here we have a more model-independent approach where we just have a cosmographic expansion of the Hubble parameter as a function of redshift. And what we find here is that when we do this in a self-consistent combined way, we get Q0 that's consistent with the lambda CDM prediction of minus 0.55. So we get minus 0.59 plus minus 0.14. So that's very consistent. We don't find a very strong degeneracy with H0. We just find that the errors in Q0 increase depending on the systematics that we account for. And the cut Z case here is where we only account for the systematics between the calibrator rung and the nearby Hubble flow, which is what is used in the shoes analysis. So we can see that when we account for the calibration uncertainties between the or the uncertainties between the calibrators and the high Z, we start to see a slight broadening of the contours for Q0 as is expected. So this is also showing that even in a model independent way, it doesn't shift the absolute value of H0 very significantly. So given that I mentioned the sources of systematics coming from photometric calibration, as well as like understanding dependencies on environments, what I wanted to talk about was ongoing work with the Zwicky Transient Facility, which is an untargeted search and follow-up on a single photometric system to find a large sample of type 1e supernovae in the nearby Hubble flow, but also like we'll be observing very nearby type 1e supernovae for the distance ladder as well. So ZTF is a wide field 47 square degree camera survey on the Palomar 1.2 meter Austin-Schmidt telescope. It improves upon its predecessor IPTF by more than an order of magnitude, scanning about 3750 square degrees per hour. We have a dedicated classification machine, the SED machine, on the Palomar P60. And as of ZTF phase 1, there were about 5,000 spectroscopically classified supernovae, of which about 3,000 were type 1As. So with quality cuts, this would be around 2,000 to 2,200 type 1A supernovae that can be used for Hubble diagram studies. Phase 2 of ZTF has begun as of November 2020, and we have a very similar discovery rate to phase 1. We're also gaining because now we already have the references made, and pretty much having the classification rolling from the first phase of the survey. So the year 1 sample of type 1e supernovae is about 800 in the Hubble flow. So this is between redshift around 0.015 and 0.1. So the total, as I had mentioned, is 3,000 type 1a supernovae from the 2.5-ish years of operations. It's an all-sky sample, so this is important for large-scale structure studies. So measurements of F sigma 8, for example, so to arbitrate the tension on growth of structure. We can also do anisotropy studies. So with ZTF alone, we can have a study of directional dependence of H0, can do bulk flow studies and look at peculiar velocities and have a very good handle on local large-scale structure with the phase 1 sample of 1As. And it is also a test bed as well as a legacy sample for future high redshift surveys where we can do, say, directionally dependent dark energy with the high redshift coming from the Rubin Observatory and Roman Space Telescope. Additionally, since it's an untargeted sample, we are sampling the underlying distribution of host galaxy properties. And as a result, we can also probe what the impact of the environmental dependence on the Hubble residuals of the 1As are. And for more details, I won't go much into it, but you can see Mikhail Rigo's talk. So more details on the year 1 sample. So the first sort of cut that is something I'll also talk about on the following slide. We analyze the sample where we already have a spectroscopic redshift of the host galaxy. So from the 800, that is the most significant cut and takes us to about 310 1As. What's interesting about this sample is relative to the current low Z, the median redshift is higher by about a factor of 2. So it's about 0.06 compared to 0.03 in the literature. This is interesting because this makes us more sensitive to have sort of constraints on the bulk flow velocity to a larger depth and see whether or not there is, for example, an additional contribution from something more than just the great attractor and the Shapley concentration, which has been seen in the literature. So we can also probe, okay, what is like the contribution from, say, the Sloan Great Wall. So from the 1A distances point of view, we also discover them significantly earlier than in the literature. So by about a delta of 10 days earlier. And this is important because there have been papers like Hayden et al. From a couple of years ago, which have suggested that using the rising part of the light curve as an additional width parameter on top of the falling width parameter is something that's an improvement upon the standardization that is currently done within the SALT-2 distance model for 1As. And that's something that we can uniquely test with this sample because of how many of our sample have this very early coverage to then be able to retrain the light curve fitter. We also, as is seen in the example here, have coverage that goes well beyond the SALT model, which is 50 days post-peak. And we can then also use that part of the light curve in order to see how much we can improve the distance uncertainty. So we get like a complete coverage from very close to first light to much after when we have the defined model as of now. Additionally, like in the H0 measurement for the nearby Hubble flow, because we have a higher median redshift, we also have a reduced contribution from peculiar velocity uncertainties at that redshift for the Hubble flow. So since like we don't have the final calibration, this is the farthest point in cosmology we go to is to calculate the Hubble residuals. This is consistently marginalizing over the trip relation parameters, so the width luminosity and color luminosity relation. And this is, as I mentioned, with the 308 type 1As that we have with existing host redshifts. So there's about 400 supernovae that don't, as of now, have a host galaxy redshift, and the rest that's sort of missed out from the sample is based on quality cuts. And however, this is not something that is time critical in terms of the survey duration, so we can get these afterwards, and we're already like in talks with surveys that use multi-object spectrographs, so that like we can use 1 or 2 fibers in order to get redshifts of host galaxies of ZTF supernovae. And this is something that I would be very interested to talk to people about with regards to getting more spectroscopic redshifts of host galaxies, because it would be an interesting synergy while not being time critical, so it doesn't like hurt other survey pointings. We're talking about the gold sample. So we make the standard selection cuts with respect to light curve quality, as well as the like the salt to distance parameters, so with the light curve width and the light curve color. Our gold sample is about 205 type 1As after these cuts. They are all homogeneously observed from the untargeted survey. And however, like with the caveat that this still isn't like with the final photometric pipeline. And we just wanted to have like a check of what is the sigma RMS with respect to the literature sample, and we get something that's very comparable to the current low Z. And that's something that's quite heartening for us to see, because we still expect a lot of improvements in our photometric pipeline, but we would also like expect improvements when we have like the full Hubble residuals versus host galaxy properties analysis, which is seen in the literature to improve the RMS and the intrinsic scatter. We also consistently marginalized all the width luminosity and color luminosity relation parameters with the intrinsic scatter, and we find an intrinsic scatter of about 0.13 mag, and that's something that's quite interesting because again, it's comparable to the literature, and we've done this without just like fixing it to a value that gives a chi-square of 1, and that's a slight difference from what's done in the literature. So going from a probe that is essentially testing cosmology in the low redshift universe from H0, as well as going towards directional dependencies, to type 1e supernovae in a different way that would be important for H0, which is via strong lensing. I'll be talking now about the first strongly lensed type 1e supernova from the intermediate Palomar transient factory, the IPTF16GU. And basically just starting with a bit of motivation for why time delay cosmography and why is it particularly interesting to want to find lens supernovae. So the idea was originally proposed by a Norwegian astronomer, Sjur Refsdal, in 1964, to use time delay distances to measure the expansion rate of the universe. So the equation here is essentially showing the two components necessary to get the time delay distance, which is effectively 1 over H0. So we need an accurate time delay and a lens mass model. Also, additionally, we do need to model like the stellar kinematics in the deflector galaxy, but I won't go into details of that. I think Tom's talk has covered a lot of that, so just refer to his talk. Lens quasars and time delay distances to the sample from the TD Cosmo collaboration has presented a value of H0 that's good to about 3% or a bit better. Why is it that we want to look at lens supernovae? So lens supernovae are extremely complementary to lens quasars. So they have very well understood light curves and SETs. This is because of their inherently uniform nature as a population. Additionally, there's a lot less monitoring required to get a robust time delay. And having a standardizable luminosity means that we can directly get a lensing magnification, and hence like look towards breaking modeling degeneracies that are a large source of systematics, so like the mass sheet transformation as seen in the recent TD Cosmo papers. And additionally, we the way it was discovered is through the lensing magnification itself. So it's very complementary to discoveries of lens quasars, which is via the multiplicity of the images. So this is testing things like if we have image multiplicity and there's a potential bias from just finding high angular separation events, this is something that would be very complementary, because here we can find arbitrarily low angular separation events because we're finding them based on the lensing magnification, and then can trigger space-based resolved follow-up. So that's something that makes it highly complementary to the existing work on lens quasars. So IPTF16GEU was discovered exactly through that, which is, so it was by Ariel in October 2016, where it was seen to have a spectrum that is very much like type 1e supernova, where it was redshifted to a redshift of 0.4. So that was already like interesting, because finding a redshift 0.4 type 1e supernova in IPTF would probably already start signifying that there might be some magnification to be able to cross the detection threshold. So we've seen that it was about 50 times brighter than a normal type 1e supernova at the redshift. And that was about a 30 sigma outlier. So that probed or merited more follow-up. So with higher resolution spectroscopy, it was seen that you could see both lines from the deflector and the host galaxy. That led to triggering the Hubble Space Telescope and get resolved photometry in multiple filters. So this is an image courtesy Joel Johansson, who's at Stockholm, of the resolved RGB combination for the supernova on the left, just the host plus lens, and then the subtraction, which is something that's really cool because this is a transient that's not persistent. So you can actually have a cross-check of the lens model based on just the host plus lens. The individual resolved light curves, which is seen in the panel above, is something that's really interesting in terms of like measuring extinction in each individual line of sight. However, what we see is that the time delays are not very sort of long in order to get an accurate estimate. So that's making this system not the ideal in terms of measuring H0. But what's really interesting is that the magnification is really high. So the preliminary estimate was about 50. However, with extinction correction in each line of sight, it's actually closer to 70, so 67 plus minus 3. And the reason why we can measure this really precisely is because we have the resolved photometry to measure extinction properties in each line of sight, because we have a long wavelength coverage for each individual image. And therefore, we can actually constrain what the extinction properties in each one of images 1, 2, 3, and 4 are, and which is in and of itself really interesting to do that in multiple lines of sight for a galaxy that's at redshift around 0.2. So what's interesting is that while this is not the ideal system for H0, it's really a unique sort of probe of the inner kiloparsec of the lens galaxy. The very high magnification is something which would be interesting to see with a large sample of lens supernovae. So does it deviate from predictions of the magnification falling from the 1/μ³ distribution? Or is it something that we're just seeing as selection effects? That's something that would be very nice to model when we have a sample. Additionally, as I was mentioning, we can measure the extinction in each individual line of sight. This is particularly interesting in the case of 16GU because it's a very symmetric configuration. As a result, the time delay is quite small, so which is a negative from the H0 point of view, but it's really interesting from the actually detecting the systems and like studying them, because that's what gives the high magnification. However, what we expect is because it's such a symmetric configuration, from the lens macro model, we see that the flux ratios, this is in Motzel et al. 2020, are expected to be very similar for all 4 images, whereas they really are not. And what we did was we fitted for extinction from different extinction laws and keeping the total to selective absorption ratio as a free parameter. And we didn't find that changed the relative flux ratios at all. However, or rather, like it didn't account for the entire difference in the flux ratios. That's a way of putting it. And what we then saw was that if we have a microlensing from the individual stars in the lens galaxy using a stellar network, a magnification of image 1 and a demagnification of images 3 and 4 in combination with the differential extinction could explain the difference between the observed and the predicted flux ratios from the macro model. So that's something that's quite interesting. Again, for that, we do require the multi-band follow-up for each of the individual images through a resolved either ground-based AO or via space-based follow-up, and do it in multiple bands so that we can have good constraints in the extinction parameters as well. So for the last part of my talk, I basically mentioned the ongoing search for lens supernovae with ZTF. So we're currently looking at the GNR public data as well as the GRI partnership data for potential candidates that would be consistent with the light curves as well as host properties of lens supernovae. So this is basically comparing existing galaxy lens colors to what is there for field galaxies, as well as what has been seen for the two systems where we have a strongly lens type 1e supernova. And we had spectroscopic classification time with P200 and Keck, as well as P60, but that's too shallow. So what we're currently looking for is a deeper spectroscopy for vetting potential candidates. So the interesting candidates based on their colors would also have contaminations from other interesting Cocolab supernovae that are quite red or in certain peculiar hosts. So that's something that would be interesting to vet out, because we only really would have few opportunities to get the resolved photometry for an interesting system. What's nice is the predictions for ZTF are at a median time delay of about 10 days. So each supernova Tmax for the individual images can be measured to about a precision of half a day. And as a result, for the 10-day time delay, we would get a very precise estimate of the time delay, and the main sort of dominant uncertainty would not be from the time delays, as was the case in 16GU. And the plot on the bottom right-hand side is approved Muse and Hawkeye programs for this cycle, but we'd like to further propose for the coming ESO cycle, where we can see what kind of resolved light curves we expect and how well can we measure the time delays from the spectrophotometry in the optical with Muse, as well as the near infrared with Hawkeye. So we can see here that even if we don't catch them early in the optical, at least in the near infrared, we can measure a time delay reasonably accurately with the second bump, which is ubiquitous to type 1e supernovae. So right, with that, I'll just leave my conclusions and look forward to an interesting discussion. Thank you very much.